Okay. And let me share my screen. Okay, so this is what we're going to do today. So we'll go through some review of the topic we talked about last week. And then I actually was going to use Jupyter Notebook to demo some of the things included in topic 1 here. Then I'll discuss a few more algorithms. Then we move on to the topic of this week. That is from the foundation to teleportation. I'd like to see if you have any question before I go to the review. Okay, if not, let me use the poll to do the review. Okay, take a couple of minutes to give answer to this question. Okay, let's take 10 more seconds. Okay, I'll end the polling and share the result with you. You can you all see the results?
Yes.
Okay, good. So a large fraction of people feel that Deutsch algorithm is probably the most difficult over the last week. And some on the phase kickback, they are related. A little bit on the mixed day. But also a large fraction of students feel they are comfortable with all of them. But I'm going to review these subjects. So let me start share and go to the slide. Okay, so the Bloch sphere, I think most people are comfortable with this, but I want to emphasize that to describe a quantum state of a qubit, so it's a two component, right? So up and down as the basis state, but you can in any superposition, alpha and beta, and these can be parameterized with two angles. So these are, this is a spinor, if I want to use the language that often used in quantum mechanics. And this is a density matrix, the rho. So you just take a column vector times the conjugate Hermitian conjugate row vector. You get a matrix, but this matrix, it turns out, can be represented in terms of coordinate Rx, Ry, Rz. This is what represents the Bloch sphere. So the vector that it represents is a state in the Bloch sphere. Okay, and the coordinate is really related to the coordinate on the sphere. So the theta is this angle with the z-axis. Phi is this angle for the projections. Okay, and the associate matrices are Pauli matrices. These are really useful. The most important, I would say the most important 2x2 matrices in quantum mechanics. Okay, so I'm going to use an example to review. So we can ask the question, what is the state on the sphere along the negative x-axis? This state is labeled by minus. And what about the state along the positive y-axis? This state is labeled by plus I. You will see why. So the first state, x-axis, right? So x, positive x, sorry, negative x. So the theta angle for this one is pi over 2, right? And the phi angle, it all the way to that, so it's pi, right? So this state, minus state, using the spinner, this is cosine pi over 4 because there's a factor of 2 up. So let me just write as 0. E to the I phi is pi sine pi over 4, 1. Okay, so this is square root 2, 0 minus 1. Okay, so that's why there's a minus here in the labeling, right? Because that reflects the phase here. Okay, and plus I is in the plus y. You can do it similarly. Theta is pi over 2. Y-axis has the angle, phi angle. This is pi over 2, right? So this state differ by the minus state just by the phase. So the difference is here. So this is e to the I pi over 2 is just the I. So that's why I use the I to represent that. And you may also try yourself the negative y. Phi is pi over 2, add another pi, right? Another pi angle. So you will get minus I. Okay, that's the Bloch sphere. Next question, how do we use the quantum state to obtain these state from, let me just keep this, let me lower this point a little bit. Okay, so the question here basically asking how do we get this state, these states? So starting from 0, so remember we talk about 0 using the Hadamard gate. We get 0 plus 1. But if we start with 1, 1 can be using the CNOT gate to flip, and then you go through the Hadamard gate, you would get this. Right? Remember, Hadamard gate has a matrix representation 1, 1, 1, 1. How do I? 1 minus 1. Okay. So 1 minus 1, the second column basically give this, okay? And how do we get the minus I state? It's really just a phase factor I added to here, right? This is actually represented by the so-called phase gate. With diagonal element 1i acting on minus. Okay, just a remark on the zoom. If you feel something is too small, you can go to your setting. You can actually view the screen with 200 or 300 times larger. I hope you know this, how to do that. Or if it's too small, let me know, and I can see if I can amplify that on my screen. But you could do that also on your end. Okay, so basically here I introduce another gate. Let me put it here. It's 1i. Okay. Let me move on to the next one. Another example is how do we, this is about mixed state. So mixed state, you can regard that as a mixture of pure state. Okay, so how do we represent equal weight mixture of this? I mean, it's really simple, symbolically equal weight, right? So half and half. How do we mix them? We'll write really just in terms of density matrix. Okay. So yeah, so this really is the mixture. And what this means is really in terms of vector, this vector of rho, I just use subscript to represent, I'm representing rho is really just 1/2 of the vector for the minus and adding the vector for the I. Okay, it's really just taking on the sphere, taking the minus vector and the I vector in terms of the projection. This is minus. So I'm on the XY plane. This is the plus I. You basically just add the weight these two vector and then add them. So in this case, it will be somewhere here. So this is mixture. Okay. And you can write, if you want, you can write down these vectors. Okay. Because you know the angle theta and phi, you can write down the vectors. So another example. This is what I did not emphasize last time. So I talk about mixed state being mixture of pure state, but mixed state can also arise from entanglement with other system. What I mean is that suppose I write this is really a 2-qubit. Okay, 2-qubit state. I have a minus state, but I want to actually derive it from an entanglement with other system. So this is my state with minus, but this is my state with I. I want to use maybe other system, let me call it environment. If I sort of entangle my system and environment with appropriate weight, then when I ignore, let me just put quotation, ignore, more precisely, when I trace over the environment, I get mixed state for the system. Okay. So let me not go to the math detail because I just want to introduce this notion here, but we can talk about that later, about how do you trace over. You know the trace of a matrix, but this trace will be traced only the part on the environment. We'll get to that later. Okay, any question? Okay, so another review topic is observable and measurement. So I talked about last time, measurement, we usually refer to as strong measurement. It projects wave function and the outcome is probabilistic, but you also need to define how you want to measure or the observable that you are measuring. And that is equivalent to this prescribing a basis. So in this particular example, the measurement is along this axis. So what it does is you are given with a wave function, it's in a superposition, but when you perform the measurement, the observable is described, in this case, described by Z. So remember, this is what we talk about. This is along the up and down axis, and +1, -1 are simply what you're going to measure, the value you're going to read out, and it's kind of scoring system. So it's will randomly, when you perform the measurement, randomly output up or down. So they're really random. Okay, and here describe the probability of that it occurred, right? So if a state is really just up, when you measure, it will always be up. But when it's in a superposition, you have some probability of getting the outcome to be up and some probability of getting the outcome to be down. Okay, so in some sense, if this system, if I extend this a little bit, so now suppose consider the 2-qubit example, very similar to the previous one, the system and the environment. Suppose system and environment, suppose it's alpha up 0 for the environment and beta down, system and environment is 1. Let me just say 1. So if we measure the system, we'll get up, right, with some probability, which is alpha squared. And we also sometimes get down with probability beta squared. But when we measure up, this is the only possibility. Up and 0 is associated. So meaning the environment will become 0 in this case, and environment, in the case of measuring system being down, the environment would become a 1, right? Because these are the only two possibilities. So this, in this sense, emphasizing the collapse of the wave function, so projection. So when it projects the up, the environment can only be 0. And when you project the system to be down, the environment can only be 1. Okay. The example, what is when you have observable being X, right? So X is in this matrix, and in the exercise, you're going to diagonalize this, and you will see that this is actually plus minus. So the axis is actually defined this way, right? And the probability of measuring up is basically taking the wave function as a vector and then dot into the plus outcome. And the probability of measuring minus is taking this wave function dot into the minus. So this also shows using Dirac notation is really useful, but you can immediately see that. Okay, any question? Okay, so another review topic is the control NOT gate. So last time I defined that when the first qubit is up or 0, I really apply the identity, and with down, I apply the NOT gate. And you can actually see from the basis state how it transforms. If it's 0 and the second bit is 0, it really just remains 0, 0. If it's 0, 1, it's still 0, 1 because the first bit is 0. But when the first bit is 1, 0 gets turned into 1, 1 turned into 0. This is what the NOT is doing. Okay. So we have that if you start with up, up, after the Hadamard on the first qubit, it put it into a superposition. And when you have a control NOT, control is on the first bit. And this would flip the second bit when it's down. So you get entangled state. Okay, so this is probably the first quantum circuit we have. You start with 0, 0 and Hadamard, control NOT, and this is the output state is 0, 0 plus 1, 1. Okay. Any question? Received? There might be chat. Yeah, if I forgot to read the chat, maybe somebody else can remind me. Okay. The first is, so if we travel down along minus side, we get minus 1 instead of 1. I guess you're referring to the previous, the minus state. The minus state, move this away. Yeah, the minus state is really 0 minus 1. The plus state is 0 plus 1. Of course, there's a normalization, 1 over square root 2. That's the first message. Second message, Y is considering only one such system equivalent to taking the trace out of the other system. Yeah, so here, this is a very good question. So this is next page. So because when we describe a system, if we have no knowledge of the environment, if we only have access to the system alone, so for example, it might be coming out, might be arising from an entanglement with a subsystem, let's say environment, but we have no access to the environment. So that's why we need to trace over or ignore this in order to describe the system itself. But this system could also be that it arises from a mechanism that the source is emitting minus or plus I half of the time. So without accessing to the environment, we have no way of how the system actually is generated, unless we know how, unless we specifically generate using probabilistic emission of different states. Okay. And if you only have access to the system and you are measuring an observable, right? So if you're measuring observable of the system, you will write as trace of any observable times the state itself. It's the same. It will be the same as you take this 2-qubit state and then measuring the expectation value. There will be no difference. Okay.
In the pure state psi, shouldn't OS tensor with another identity?
Yeah, so
for it to make more
yeah,
sense.
so if you want to be rigorous, this will be identity with the environment. Okay. See other chat message. So do we get the mixed state by adding 2 or more pure state in different bases? Yeah, so you can add, but add not in the sense of adding superposition, add in the sense of mixing them. So basically probabilistic mixture. Okay, another message, not necessarily different bases, just different pure state. I guess this one is answering that chat. And then the reply, won't that be just a superposition? So I emphasize it's not a superposition, it's really mixture. So superposition we can write in terms of cat alone, but mixture we really need to have a statistical like weighting them. Let's see how do I go back? Yeah. So you really need to mix them. This is how we mean by what we mean by mixing. Right, this is really mixing. If you write this and that with some weight, then it's not mixing. This is not mixing. It's superposition. But this one you have to be careful, alpha, and because I and minus state, they are not orthogonal. So alpha and beta are not necessarily, their sum is not really just one. Okay. Okay, so let's now move on to the phase kickback. So this is the circuit that I described, and this is really general. You have a 2 register, X and B, and you have a unitary UF. What it does is really just taking X, evaluate the function of F, X, and adding it to the second register, B. Adding, in a sense, I'm going to say that it's really bit by bit adding. For example, 0 adding 1 is 1, 1 add 1 is 0, 0 add 0 is 0. So bit by bit. Okay, if you have many bits, you add bitwise. So the phase kickback is that if you send in a really special B state and really the 0 minus 1 state, what you do is that you consider the effect, right? You just write this f of x plus 1. Then just by considering 2 possibilities, so f of x could be 0 or 1, then you can actually encompass the 2 cases in one equation. Basically, that if f of 0, you can verify, right? You can verify yourself. If f of 0 is 0, this phase does not exist, and that's 0, 1. But if of x, f of 0 is plus is 1, that actually flip. So this will become 1 and 0. But 1 and 0 is opposite, has opposite sign of 0 minus 1, so it's really reflected here. So this is one example of phase kickback. You may, in some other cases, you may send in some other states, but maybe the general principle is this state is some eigenstate of the system. So in fact, this is, this is minus 1 eigenstate of X operator. Okay, so phase kickback basically says that the phase factor can be just included here, and you forget about this. Really just forget about this. Okay, so this is easier for you to analyze, right? So then I can totally forget about the B register. So I can get the X coming through the black box. It acts as if there's an additional phase factor. So I can forget about the second minus input. This is the essence of phase kickback. And we use that in the Deutsch algorithm. So, right, so we just need to analyze. Right, if we send in X as a plus state, according to the phase kickback, right, this is the phase kickback. It's -1 to the f of 0, and then the second term is f of 1. If it's constant, they're all the same. Right? Up to this factor is a constant, so it has a plus sign. If it's balanced, the two functional values are different. Therefore, there's a minus sign, right? And this is the way to distinguish the two cases. Right? So you just need to measure in the plus and minus spaces. Then you know whether it's constant or balanced. Okay. Let's see. There seems to be a chat. Okay. Yeah. Superposition is adding 2. Okay. Somebody was just reminding the previous discussion. Okay. Okay. Let me move on. Yeah. So you can actually generalize the Deutsch algorithm to n qubit. So I'm just drawing with a /n, basically just to represent that there are n lines. There are n qubit, okay? So this is a generalization of the Deutsch algorithm to the problem where it's promised. So if we are promised the f is either constant or balanced, meaning half of the input you get 1 and the other half is 0, then you can actually construct, you can always send in this, and then the analysis will be just on the X register. But this just generate the previous consideration to n qubit. So I won't do this. This is going to be an exercise, but I want to emphasize that when we use the Hadamard gate, right, we turn 0 into 0 plus 1 and 1 into 0 minus 1. And you can actually simplify by writing this. S can be 0 or 1, S1. And you write that the action of H on arbitrary S1 is arbitrary S1 being 0 or 1 to be this identity. Okay, so they're really just summing over all possible cases. And this -1 to the S times Z is just taking into account the plus sign and minus sign. Okay. And in one of the homework problem, you're going to extend this. So when I use this, I simply just say that I'm just use a notation to simplify writing down all these. If I take this and act on S1, S2, n of them, you could generalize this to 2 to the n and sum over Z1, Z2 up to Zn. This will be sum over Si, Zi. And let me erase. And this will be Z1, Z2 up to Zn. Okay, so just to convince yourself that this is the case in the homework exercise. And so this this will be another exercise, but maybe for the next week. So here you're going to consider the Deutsch algorithm generalized to n qubit. This is called Deutsch-Josza. And if this is a constant, you measure the n bit of x in the plus and minus basis. If it's constant, you will always get plus, plus, plus. But if it's balanced, then you get something that has at least one minus. So it will be orthogonal to that. So you can distinguish the two cases. Okay, but you will do that in your homework, the next homework. Okay, any question? Okay, if not, then I'll talk about a more general case. And this is where you see you can actually exploit the quantum parallelism. So how do I see that? So I have the same circuit, but x can be n bit, right? As in the Deutsch-Josza algorithm. Suppose I send in the x register being in a superposition of 0, 1, 2, etc. So this is really the 1, meaning that it's 0, 0, 0, 1, etc. I'm using this to represent. You should think of it as a binary representation of the number. And the B is in 0 state, right? According to this rule, the output of the state will be 0. The second bit will be f of 0 plus 1, f of 1, 2, f of 2, etc. Right? So here you see a massive parallelism, because if x is my question, f of x is the answer, then inside this quantum circuit, the quantum state actually encode the question, answer, question, answer, and question, answer, right? It's as if the quantum computer knows everything. So this, the so-called parallelism, it's actually using the superposition, right? Using the linearity that we talk about, one of the 3 rules of quantum mechanics. This shows that quantum computer can be potentially very powerful because it knows everything. It embeds all the question answer in a quantum state. However, there is a complication. So to get some answer, we need to perform measurement, right? So this is also the 3rd rule of quantum mechanics that come into play here. To read out, we have to measure. So for example, I measure this register. So I have the superposition of k into this, and output is also a superposition. But here you see that it's an entangled state, right? The question and answer are entangled. But when you perform the measurement, let's say we perform in the usual computational basis, I may get k, right? This x I measure and get k, but according to the measurement that I just illustrated earlier, it collapsed the second bit, the second register to be f of k, right? So this is the question. I collapse the question, and the answer is collapsed to f of k, right? So only one answer at a time. And this may not be what you need, right? Maybe I actually need k prime, but I get k. So somehow it's worse than the classical computer because k is random. So this is a dilemma, because by measurement, we are getting only limited information, right? Even though the quantum computer may have all the question answer entangled, but to read out, we sort of need to collapse. However, we can also measure in a different basis, right? Or even we can measure the second register. So let me just illustrate. Suppose we measure the second register and we obtain the answer to be f of 0, right? Because of measurement, it collapsed the second register to f of 0. It would also collapse the first register. So maybe the question to you is, what is the state of the first register? Right? By just thinking a little bit, you realize that the first register will be in a superposition of all those x, such that f of x evaluate to f of 0, right? So with this, you might be able to figure out maybe the symmetry property of f of x, the period, etc. So this actually is the essence of quantum algorithm. namely most quantum algorithms try to find a smart way to perform the measurement, or try to find a smart way to process the quantum state before you perform the measurement. Okay. Yeah, so maybe I want to stress that quantum computer may not be useful to perform addition or multiplication, but it is going to be extremely useful to determine the property, symmetry property of a function. Okay, so if you can understand these two slides, you will really get the essence of quantum computing. Okay, so there are more quantum algorithms. The most famous one is Shor's factoring. And the second probably is the Grover searching. Shor's algorithm has an exponential speedup. Grover has a lower one, it's only quadratic. And there are more algorithms. So I'm illustrating one. So you might wonder if I have a matrix equation A times a vector equal to B, is there a way to solve this by a quantum computer? And indeed there is one. And the speedup can be exponential, but it depends really on the matrix of A. So we'll be covering these later in the course. But there is a zoo of algorithms. You can check how many quantum algorithms are there. Maybe over 100. Okay, so I said earlier we're going to see a Jupyter Notebook demo. But I want to emphasize you don't need to know the detail. This is just to illustrate. And for those who knows Python and Jupyter Notebook, you can download and play with this. So it's here. Let me share my notebook. Can you see the notebook?
Yeah.
Yeah.
Okay.
Yes.
So it has some detail, but you need to load required packages. So doesn't matter that much at the moment. So I'm just want to illustrate that I define the 3 Pauli matrices. You should recognize these 3 matrices. The I here in Python, you have to write 1J. And here I define a function that map a spinner. This is a spinner as an input that I turn it into Rx, Ry, Rz. So it basically just writing out the Rx, how it evaluate using the spinner and the Pauli matrices. Okay, suppose I convert the spinner to a vector, 3-dimensional vector, then I can use the function that already designed in the Qiskit. It's called plot Bloch-Sphere. I have a spinner 1, 0, which is the 0 state. I use my function Bloch vector to convert into a 3-dimensional vector. This Bloch vector basically plot the arrow. Okay, so you can see this is a 0 state. This 0, 1 as a vector is 1 state. So I see that this is 1. And can you recognize what state is this? 1, 1 as a vector.
Plus.
It's the plus state, right? So, and it's pointing in the x direction. And you can imagine this is a minus state with a minus sign, by pointing in the opposite direction. And now I put an I here. So this is pointing in the y direction, plus y direction. You can expect if I put a minus sign, it will point into the opposite direction, right? Okay, so that's the Bloch-Sphere. And I want to emphasize Bloch-Sphere only works for 1 qubit. So, and there is a function that called Qsphere. Qsphere can actually represent multiple qubit states. but I want to illustrate by drawing the quantum circuit. So suppose n equal to 1 is 1 qubit. I say I just define it as a quantum circuit of 1 qubit. I call it QC. I can draw this circuit because I just initialize that, right? So it's really just nothing. Assume this Q, the state of Q is 0 in the beginning. Okay, so what I do is I read out the state vector. It doesn't matter the detail. I mean, you can play with the code, you can change that. So I read out the state vector from the quantum circuit, and I plot the state vector in Qsphere. Right? So I see this. I mean, I could also plot in terms of Bloch sphere. So I need to evaluate this. Okay, so this I plot in terms of Qsphere. Right. So this Qsphere is similar to the Bloch sphere. Right. It's pointing up as a 0 state, but I could also use what I have here to plot. Okay, I can take this state vector and then plot that. So let me insert a cell and then says the input is my state vector. Okay, so it will give embedded syntax. There's one more. So it's giving the same. At the level of 1 qubit, it's give the same. So I can also see how the quantum state evolve. Right? So I apply this syntax, basically quantum circuit dot h, meaning that I'll apply a Hadamard gate, and 0 apply Hadamard gate will turn into plot state, right? And so when you use that to plot the Qsphere, it's really just giving you 0 and 1. This is the superposition. So it's not showing the same as the Bloch sphere. So there are some differences. Okay, let me just execute this and plot, right? So this is the feature of Qsphere. But if I use a Bloch sphere, I would see that it's pointing in the x direction. Okay. Basically, the Qsphere is keeping track of the superposition. Here, north pole is 0, south pole is 1, and the phase factor is all 0, so it's in a plus superposition. Okay. Then I could also apply a S gate, right? Apply S gate. Remember in the example earlier, if I have an S gate, it becomes an I state. So if I use the Qsphere, it's 0 and superposition of 1, but the 1 has a phase factor you have to read out from here. It's pi over 2, so it's really I. But I can also plot using the Bloch sphere. Did I execute? Yeah, okay. I plot this. So this will be I state. Okay. And I can go on and using the 2 qubit because Qsphere allow you to plot more than 1 qubit. Suppose I have a quantum circuit, 2 qubit. So I initialize all in 0, 0 state. I apply Hadamard gate to qubit 0 and control NOT gate on the first and second qubit. So 0, 1 qubit. I draw this and I can plot the state vector. It's also similar to the plot state because now north pole here is 0, 0 and south pole is 1, 1. So that's the feature of the Qsphere. But I cannot draw this using using the Bloch sphere because it's only one qubit. Okay, so Qsphere is a new way of representing the quantum state. If you don't understand that in detail, it doesn't matter that much at this point. But I just want to introduce the code that you can download and play. And one nice thing about this, if you have a quantum circuit, you can say, I want to perform the measurement. It will measure in a 0-1 basis. And I can say, what is the outcome statistic? For example, I just create a 0, 0 + 1, 1 state. If I measure, I should, in principle, get 50-50. And this simulation, of course, you have some statistical fluctuation. It's not exactly always 50%, but it will be very close because we only repeated the measurement 10,000 times. Okay, so I'm not going through all the circuits, but just to show you that if you have more than one qubit, so this is 2 qubit, you know it's 2 qubit because there is a circle and there are also north and south pole. If you have 3 qubit, this is a 3 qubit circuit, you will have 2 circles. So basically the number of circle is the number of qubit minus 1. Okay. Yeah, so let me leave the Qsphere, but I want to illustrate the Deutsch and Deutsch-Josza algorithm. Any questions so far?
So with the simulation of the probability, is it actually done in a quantum computer, or is it just
I'm using the simulator.
they
have a program that can simulate the effect of measurement. Yeah, okay. But you could also run it on real quantum computer. Okay. As I'm going to demonstrate the Deutsch-Josza algorithm.
Okay.
Okay, so it doesn't matter what these is really standard. You just copy the code, including necessary packages. But to run on actual quantum computer, you need to have an account. So that's why I encourage you to register with the IBM Q. So here, let me show you the circuit. So this, you should by now be familiar with this circuit, right? This is the X register, this is the B register, but I always put it in a minus state. And I tell you how I do minus state. I turn it into 1 and then using the Hadamard, right? So this was the example that I showed you earlier. And this is always the plus state. The reason I have to use these circuits is because quantum computer, they always initialize in a 0 state. So that's why I have to do it by hand. And this is the function U of F. And whether it's balanced or not is really measuring the plus and minus basis. But quantum computer, they only measure in a 0-1 basis. So I have to turn it into convert this by the Hadamard gate to the 0-1 basis, then I measure that. So if it's a plus at this point, that meaning that it's a 0 here, then it's going to be constant. And if it's 1, then it's going to be balanced. Okay, unless you have a question, please don't annotate. If you have a question, you can ask, and then if you need to annotate, let me know. Okay, so that is defined here, but let me show this. This block is usually called oracle. Oracle is doing some function, some actions, so it's defined as an oracle. You can regard it as a black box. And here I define the oracle. So it's not that important, the detail, but if you're interested, you can see how the balance is designed and how the constant is really simple. You just always output the same state, or you flip, or the output is always the same. And this is the algorithm. So you start with the circuit. So here we can use n qubit. So n qubit will be called Deutsch-Josza. So I have an n qubit as a register. I have an additional one that I need to use the phase kickback. So I have n plus 1 register, and my x register is n bits. So if I measure that, I need to store the n bit information. So this is really just prepare everything in the plus state for the first n qubit. The last qubit is always in the minus state, right? This is how it prepared. So the argument can allow you to test whether it's randomly giving me constant or balance, or just allow me to assign balance or constant. Okay, so depending on whether it's balance, I use the corresponding oracle, and then I perform that actions, and then we perform the measurement, so the readout. So basically at the end, this is what the circuit is. So I just say I have a quantum circuit implementing Deutsch-Josza algorithm with n equal to 1 qubit. This is the circuit. Here we can first use simulator. So I use simulator, and then I perform the measurement. Of course, I'm using the constant, so I should always get 0. And simulation always shows that. But if you now run on real quantum, this is the quantum computer that I use. It's called Berstein. And if I run that, this is what you see on the actual quantum computer. Supposed to be 100% 0, but it has some 13%, 14% of 1. So this means that the quantum computer is really noisy, that you don't always get the right answer. Okay. Okay, so this is just plotting the output. This is the minus state. This is the first qubit is the plus state because it's a constant. This is from simulator. Okay, so that's the demo, but you can play with that later yourself. So let me yes.
So the simulator can simulate the error of the actual computer.
Yeah, you can download some error model, and then you can simulate. Okay, so let me return to the slide. Okay, so there are two other algorithms. So this one is very similar to the Deutsch algorithm. So I'm considering a 1-bit function. So this is one bit to 1 bit. Okay, so f of x is a times x. So a is 0 or 1, right? So if a is 0, f of x is going to be 0. If a is 1, f of x is x. This is a very simple function. So what it asks is, suppose I have a black box, or let me call it oracle, implementing this and add compute and then add the answer to the second bit. I want to know whether the f of x is 0 times x or 1 times x. What is the a? So the goal of the algorithm is to figure out what the a is. And as before, I can just input the second register with the minus state. So I just need to use the phase kickback. And the first register, I'm going to use 0 plus 1, the plus state. as input, just like the Deutsch algorithm. And the phase kickback tells me that this is what I have. If A is equal to 1, then f of x is x. And it's actually a CNOT gate, a control NOT gate. Because if A, so f of x, so meaning that if it's 0, then f of 0 is 0. So meaning 0 is doing nothing, right? And if it's 1, f of 1 be 1, because you would add this to B, but 0 is really adding 0 is no action. 1, you add 1 to B. This is to flip. So this is the action is a CNOT gate, right? So if A equal to 1, this black box is actually implementing a control NOT. Okay. Yeah, so if it's a control NOT, or you just use the property f of x is x, then this will be 0, this will be 1. So f of x. Then there is an additional minus sign, so you get a minus, right? When A is 0, then it's a plus state. Right? So I'm just plotting all the circuit here, so maybe I erase this. Okay. So meaning that it's similar to the Deutsch algorithm. You just measure in the plus and minus basis on the first register. If it's minus, you know A equal to 1. If it's plus, you know A equal to 0. Okay. And you can generalize to the n bit. So that will be very similar. So let me not go through the detail here, because A dot x is really sum over A1, x1, A2, x2. It's really just independent. So you can do similar measurement here in the plus and minus basis. If you read out a minus, that means the corresponding bit has 1. Okay. So that's the generalization. So if you don't understand the n bit, you should go back to the 1-bit case, and then you understand the n bit case. The next algorithm is called Simon's algorithm. I don't want to discuss this in detail, but I just want to raise some interesting observations. So this is your homework, related to your homework problem. So 0 is mapping to this, but yeah, this one is exactly the homework problem. If you have bit string S, then after the Hadamard gate, it's not like this. It's similar, but with a phase, right? Basically, if S dot Z, in the sense that this is SI times ZI and sum over that, this is really the binary addition. Right? If this is 1, that means that there is a non-zero here. That means the factor is -1. So let me just say what Simon's algorithm does. So suppose there's a function f map from n bit to some finite set x. And again, we promise that the f has these features that there is some hidden string s, so s1, s2, sn, such that if you have two different arguments, the function would evaluate to the same value. And this is if and only if the two arguments differ by a string s. So they're either the same. Of course, if you have the same, you evaluate the same value. But if the two strings differ by an s, then it's guaranteed that they evaluate the same value. The goal is to find s. Okay, so let me just give an example. So it could be that when x is 0, 0, 0, and suppose s is 0, 1, 0, does that mean the corresponding y will be 0, 1, 0? They would evaluate to same value. Okay, so that's the goal of the Simon's algorithm. So this solution of the algorithm, this is probably the most complicated algorithm in the first 2 weeks. So I don't expect you to understand all the details, so I'm just not going to go into too much for this one. Because when we come back to the Shor's algorithm, we will also discuss something similar. So the point is that if you have a superposition of 0 and s after the Hadamard gate, you evaluate to this. And it could potentially be a minus sign factor and adding 1. If they add to 0, that means that s dot z is 1. But those that are left would be those that has s dot z equal to 0, meaning that the z can only appear in the summation if it's orthogonal to s. Okay, so you can simplify this. And so what really the algorithm does is that you prepare all the superposition. So again, so the quantum computer evaluate to the question and answer, right? And suppose you measure the second register, right? So the second register would project the first, project to F0. That means the first one will be some x0 and x0 plus s. Because we say that only those differ by a string s will evaluate to non-zero. So this writing is not so good. Just write again. Okay, hope that's slightly better. So then you need to figure out what s is. So if you perform the Hadamard gate to this, right, using what you have here, Hadamard gate on this, you only get the z to be orthogonal to s. So you just perform measurement. You perform the measurement, measure the first register, and see the value. The value wi will be orthogonal to s, right? And you repeat many, many times. So that you collect enough vector. So you collect w1 vector, w2 vector, etc. wk, let me say. The s has to be orthogonal to all these vectors. So the s, maybe s is orthogonal to everything. Okay, so you can figure out s. Okay, so this is probably the most complicated algorithm we have discussed so far. So it probably takes some time for you to digest. So, but let me pause here to see if there's any question. Okay. If not, I'd like to go to the material of this week. It's from foundation to science fiction teleportation. So we probably only have time to cover the so-called Bell inequality. But the point of this week's material is to demonstrate that quantum entangled states have correlation stronger than classical states. I forgot to add the word stronger. Oh. Let me add the word stronger. Then I share the screen. Yes, first I'm going to demonstrate that quantum entangled states have stronger correlation than classical. And then later in this week, maybe next time, I'm going to also show you that quantum entangled states not only have stronger correlation, but also are useful as well. So useful. So they can perform things that classical mechanics cannot do. So to discuss the Bell inequality, let me remind you that when we perform measurement on these Pauli operator, right? If we perform measurement, we always read out plus and minus 1. So we read out, right? And it also holds true if you really just rotate along any point in this Bloch sphere, right? So in the Bloch sphere, any axis that you get, you would define a plus 1 and minus 1. This could be some direction r, as long as r is equal to length 1. So you get plus and minus randomly. So there's an interesting mathematical formula. Suppose I have 4 variables, a prime, b, and b prime. They can only be plus and minus 1. I want to consider this combination so that it's actually easy to read this. I'm going to consider AB prime, okay, A prime B, but I'm going to subtract minus A prime B prime, okay? And you can just combine these. This is A times B plus B prime, A prime times B minus B prime. And you can convince yourself that you can only get plus 2 or minus 2, okay? Because if you consider B plus B prime, it can be if plus 1, minus 1, or plus 1, plus 1, minus 1, 1, minus 1, minus 1. What can it be? It can add to 0, right? It can add to 0. Or it can add to plus 2 or minus 2. But when it adds to 0, B minus B prime is 2 or minus 2. And when B add B prime to be 2 or minus 2, it's 0, right? So that means it's either this or this. Basically, it's plus minus 2, right? Either way. And A can be plus 1 or minus 1. So it ends up that this equality can only be plus 2 minus 2. It's really just simple algebra. Okay, just considering all possible cases. So what does this has anything to do with quantum mechanics? We're going to see that this would give us inequality. So for example, let me get my cursor back. Okay. So I'm considering this equation evaluate to plus or minus 2, but suppose I have some distribution, I have some random distribution of these 4 variables. So I can consider the expectation value. So I use E to represent the expectation value of this. But if I sum plus minus 2, etc., and randomly distribute that, and I average that, it must lie from between 0 and minus 2 and plus 2, right? If I average that, if I have plus 2, minus 2, I may add up to 0. If I have more plus 2, I would bias toward 2. But I can only be in this range. So I'm really just mathematically write this in this way. So the way this has anything to do with quantum mechanics is that I'm going to consider a quantum mechanics scenario where the choice of A prime, B prime, representing 2 choices of observable. It could be I'm measuring along this axis or I'm measuring along that axis. And A would be located at location A and B measurement done at another location B. So this means that if the world is classical, I should have these correlation EAB and for possibility and these combination plus, 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 minus, just as I show here in this diagram. They have to be lie from minus 2 to 2. That's from a classical theory. So even if you have some probability distribution. So now this is called local theory, local hidden variable. So I'm just going to make more assumption on this. So I'm going to assume there is a source. Somehow I'm going to assume there are 2 particles, send it to A and the other send it to B, and they perform the measurement. So I'm going to assume that because my measurement outcome on either side is going to give me +1 and -1. So it'll be +1 and -1. I use A, capital A of A lambda as a +-1. And rho lambda is something, some variable that I don't know, but it's sort of keep track of the distribution in the source. This is called, and this is the expectation value that I get. So really similar to this. Okay. And I'm going to perform the experiment. And if the source is classical, then I have this inequality, right? So from -2 to 2. But if it's quantum mechanics, next time we're going to show that if it's quantum mechanics, then we will get this inequality violated. And the maximum that we can have is 2 square root 2. So we're going through the detail next time. But and I'm just previewing what comes next on Wednesday. And we know what the measurement setting has to be. So on the A side, you choose A and A prime, B and B prime axis to measure. So we're going to show that this is violating this inequality. Okay, I think I'm running out of time. Okay, so I'll stop here and then see if you have any questions. Anything related to Bell inequality can be postponed to next week, next time, Wednesday. really this class, you only need to understand the equality here and inequality. Okay. So regarding office hour, it's not possible to satisfy everyone. But what I'm going to do is choose a time which fit most of the people. And then for those who cannot attend the office hour, you can send your question and then we can discuss those in the office hour. And I'm also trying to have the office hour discussion recorded. So that way you won't miss anything. And if there are really questions, you can actually bring up during the lectures. Okay, any more questions?
Are we not supposed to see any homework, even the submission option on Blackboard?
Oh, you cannot see the submission option?
Yeah, I don't even see the first homework.
Oh, okay, let me check, maybe. Yeah, let me check. So
Is
the
that the
homework
case
is
with
due
yours?
Sunday. Okay, I'll double check the homework submission. But I hope you are working on the homework. Any other questions? Okay, so if not, let's end the lecture here and see you Wednesday.
Thank you.
Thank you.
Thank you.